Welcome, Nick McQuaid here on day 10 of iste780, Data-Driven Knowledge Discovery. We've almost hit the halfway point here. At the end of today, we'll have hit the halfway point. Okay, and so today we have a lab on cross-validation and bootstrap, and we'll be doing, 5 parts: the validation set approach, the leave one out approach, the k-fold approach, the bootstrap, and an application of the bootstrap. And then you have a homework to turn in today, exercise 5.4.6. Okay, so let's get started. I've already turned on my editor here, and let me just, and I've turned on R. Let me just give my option that I think will, something wrong there. I want to match the output of the textbook, and they change during the course. They frequently seem to change the number of digits of precision that they use. So I'll try to stick with that. Okay, so the first part is the validation set approach. So let's set seed 1 so we get the same results. This is only to get the same results as the textbook. And we're going to create a training set, and we're going to do that, we're going to use the sample function, and we're going to use it in kind of an odd way. Normally, the sample function takes as its first argument the data set that you want to sample from. We're doing a little thing here where if the first argument to sample is an integer, instead of expecting a data set, it simply assumes that you want to sample from the first from the integers 1 through whatever the integer is that you entered. So in this case, from 1 through 392, and it is going to take 196 samples, and by default, I believe it's without replacement. 109, and you can just, I don't know if mine is working here. Yeah, my help thing isn't working here, but you can just check it to verify that that's the case. So we now have a sample. Let's just look at the sample for a second. Did I not run this? Yes, I did. Okay, I did not run this. Okay, so there's my sample training set. That is the indexes, some of the indexes from the auto data set. So I'm simply going to use these indexes and say data auto for my for the linear regression model I'm going to fit. So I'm going to say linear regression model LM, and this is again the miles per gallon regressed on horsepower. Data equals auto. Subset equals train. So see, these are just the indices that I just created. So this is just going to use the observations in that data set with these indices. And I may as well attach auto here. And I'm going to check the MSE here. And so what I'm doing here, so I've created the model with the training data, and then I'm checking the MSE with the test data. So this is actually the test MSE. Okay, and we can do the polynomial version. Now, there are a couple of different ways of doing the polynomial version, so we're going to do it a little bit differently. Here, I'll just reuse this. LM fit, I'll call this LM fit 2, and it's, we're going to go with, let's see, poly horsepower 2, and still data auto subset train. So what we should get here, and then we'll just do the same function here, except we're going to do it with fit2. And we see a substantial reduction, which we expect. We've already run this regression before, and if you recall, horsepower squared is better than horsepower. So previously we did capital I and then horsepower and then circumflex and a 2 to get horsepower. This is another way to do it, and in a way this is going to be a little bit better because we can isolate this 2 and make a parameter out of it in a minute. So let's just let's first do the cubic, and so that's going to be number 3, and we get, as we have found before, none of the higher powered exponents seem to make a big difference in this data set. You know, it might, but but who knows? Anyway, let's see. So the next thing that we want to do, so we've got these error rates, and we can do a different training set. So let's sample again. So I'm going to say set seed 2 this time. And I'm going to say train. Where's my train thing here? I'm going to do this again. And I'm going to do this again. And I should get a different result this time. Let's see. Is that what I'm supposed to do next for this lab? I assume this is this. So see, notice I got a different result. And now I can just manually do the same thing. I'm just going to cut and paste these though. Oops. Okay, and again I get a slightly different result, slightly better result than I got last time. And a slightly better result this time. So not a big difference, but a small difference due to random variability. Okay, so that's that for the validation set approach. Now, what about leave one out? So we're going to do leave one out. We're going to use we're going to use a different function here. So let me just where is that one? Yeah. Just going to copy that. I'm going to switch to. So in addition to linear model, there's a thing called general linear model, and general linear model has a cv.err function in it that we're going to use. So, or cv.glm method that we're going to use. And so we're just going to use this. We get the same results. In fact, here let's run it. And I think part of the lab is that we run it. Let me just say, I keep losing my place here and leave one out. Validation. And so I'm going to do this and then get the coefficients. And what you should see is that when I do the same thing with the linear model, I get the same coefficients. And of course, I get exactly the same coefficients as it should be. So the only reason that we're using general linear model is so we can take advantage of some of the functionality in the general linear model in this library, in the library we're going to use. Let's see. So we've already just done this. We'll do it again just for fun. And now we'll take the output of this other function, cv GLM auto GLM fit. Okay, and then the delta in here, actually there are two deltas, but oops, what am I doing? Did I miss something here? So I said GLM fit. What have I done wrong here? Something weird here. I don't know what it could possibly be. Let's see. So I said library boot. I needed that library. GLM fit gets GLM miles per gallon. I did do this, didn't I? Looks like I did. And yet I get NA for this. That is so strange. What could possibly have gone wrong here? I just don't know. Well, I'm going to have to pause and think about this for a second. Okay, it should have been obvious to me what my problem was, but it wasn't at all. So let me redo this. Okay, there we go. So this is delta. This is the cross-validation estimate. The reason that it appears twice is this second one is actually bias corrected, and there is no bias to correct, or not enough at least to correct in two places here. So we don't get any different. We don't see any difference here. Okay, now let's repeat this procedure for 5 polynomials of horsepower. So we're going to do a little for loop here. This is one of the few kinds of cases where it makes sense to do a for loop. Generally, what you can accomplish with a for loop, you can accomplish with vector notation. So we don't do that much. You may have noticed that we've been doing a lot of things with the subscripts of vectors. But here's a procedure we want to do that's going to make sense as a vector. I mean, as a for loop that we're going to repeat 5 times. And why did I said okay for I 5 miles per gallon regressed on polynomial, and this is what I mentioned before about taking the polynomial out as a parameter. So what we're doing is going from the 0th power to the first to the, or no, from the first power to the second power and so on, which we have already done before. So this isn't going to be any huge surprise to us. This shows how R got the results that we looked at yesterday. We saw a plot of this, of the output of this yesterday. Okay, so there's the whole thing, and then what I'm going to want to do after I run that is look at the CV error, cross-validation error. So there'll be 5 of these. And strangely, it's taking a little while to run. So the last time I did this, it says in the book that it will take a couple of minutes to run. The last time I did it, I timed it and it took 4 seconds. The time before that I did it, 5 seconds. This time I think it took a little bit more than that, although I did not time it just now. I guess I can only play this back to get the timing. Okay, and so we get the exact same results that we've gotten before, which is that going to the second power provides a much better estimate of mean squared error, but going to the higher powers doesn't really do much of anything. Okay, now having done this, we're now going to switch to k-fold cross-validation, and remember that k-fold cross-validation is a more general case of what we've just done. So, as you may guess, there's not going to be much of a difference here, except we're going to set k as a parameter here. That's really the main. And we're going to set that parameter to 10. And I may as well just copy this. Okay, so let's see, for I is 1 to 10, GLM fit gets horsepower I, CV error dot 10, I gets CV. Okay, so here's where we're going to add the K parameter, I believe. This will do us. And then instead of looking at CV error, we want to look at CV error dot 10. Okay, so is that, did I do this? No. Okay, so I'm going to set the seed to 17 so we get the same results as the book. And then I'm going to run this. And the book points out that it will run faster than did the one that we just ran. And the reason for that is we're only doing 10 times instead of n times. And let's see, we got the same results, more or less. There are a couple here that look like they're slightly lower, but that's kind of an illusion. If we run it over again, they may be slightly higher or slightly lower. Basically, the real big win is going from horsepower to horsepower squared, and we could see that. I think that was on our first or second day. We looked at the horsepower and miles per gallon scatter plot, and we saw that there was what looked like a curved relationship between them. So we've been sort of taking advantage of that ever since. Okay, now, and it says to notice that the computation time is much shorter. Okay, sure, I noticed. I think it may very well be that the first edition of this book was written 6 years ago. And I'm using a pretty low-powered machine here, but it's a 2014 low-powered machine. And maybe when the authors were doing this in 2009, they were using, a several-year-old machine, and it really perhaps did take several minutes. Okay, so that's it for the K-fold. We're just doing that one example in the lab. You're going to have to do it again for the homework. And the textbook just asks us to notice that these estimates are very similar to the estimates that we got from the leave one out procedure. Okay, so the next thing to do is the bootstrap. And here this is going to be a little bit more fun because we actually will write a couple of functions here, although they're not very impressive functions. They're little things. So we're going to create this function because the way that we do bootstrapping, we're going to still use that library boot, and we're going to use the boot function in there. The boot function takes a data set and a statistic of interest. And the textbook tries to drive home here the point that we can use the bootstrap in all kinds of situations. All we have to do is make a function that computes a statistic of interest, or just use an existing function, an existing statistic of interest, and then we just perform the bootstrap with the boot function, repeatedly sampling observations from the data set that we give as a parameter. So let's first create, so step one is creating this function. We're going to create a function that will return alpha. Each time that it's run, it will return a value of alpha. And it's going to take as parameters data and index. Now, when we give this, if we actually run this function by itself, we're going to have to supply those parameters. If we give alpha.fn as a parameter to the boot function, it's going to be smart enough to figure out these parameters, so we don't have to give the parameters in that case. Let's see. So x index. So as it happens, the data set that we're going to be using has two columns called x and y. And then a function has to return something. Does that say return? I can't. My eyesight is getting so bad. And so here is the you call it the instantiation of the formula from the textbook in R notation. That looks right. Okay, oops. Okay, so we should be able to just, once we define that function to R, we should be able to run it, and we'll run it on the portfolio data set, which we talked about yesterday. This is the data set where we chose a fraction alpha to invest in X, and a fraction 1 minus alpha of our money to invest in Y, and we wanted to figure out what the optimal value of alpha was. And it turned out to hold slightly more X than Y. The variability of X times Y was held down, and then the variability of X was held down a little bit, and then the variability of Y was the largest. Okay, so let's define this function. And then we'll run it on 100 observations from portfolio. I don't actually remember how many observations portfolio has. Let's just take a quick look. I know I could look it up. Oh, it just has 100. So yeah, and we can just say something like portfolio 1 to 5 to get a sense of what it looks like. So those are, I guess those are the returns. I can't remember I'm sort of blanking on this. In any event, you can just pause the video and go back to that part of the textbook from yesterday, section 5.2 from yesterday, to see that. Okay, so now we're going to use, let's see, we're going to sample. So we're going to use the sample function to randomly select 100 observations from the range 1 to 100 with replacement. So we're going to have the same number of observations as what we had in the original data set. But it isn't necessarily the same observations. We're going to say replace equals true, and so consequently we may have the same observation appearing several times and many of the observations not appearing at all. So we do that and we just get, oh, see, they've changed the options. Okay, and so, and I've gotten, oh, let me set seed again. That's only good for the next operation. Okay, so that gives me the same results as the textbook. Okay, so now we can really do the bootstrap here by passing this function. So that was like the equivalent of one bootstrap iteration. So let's do boot with the portfolio data set. Portfolio. That function, which R is going to be able to figure out how to pass information to that function. So we just need to say that, and we're going to bootstrap it 1,000 times, and we get an alpha of. Okay, now they've changed back again, so that they're back at alpha. So we get the same value of let me just change options to digits equals 4. And I get the same as the textbook. Okay, so I get alpha hat is 5758, and the bootstrap estimate for the standard error of alpha hat is 0886. Okay, now let's look at an example from again the auto data set. We're really milking this auto data set. Accuracy linear model. Okay, so let's say a new function called bootfn. So this isn't the same as the boot function that we've just been using. And this function, what does this function do? It takes in the auto data set as well as a set of indices and returns the slope and intercept for the linear regression model. Okay, so this is a function of data, so this is going to be this. And you don't have to, if what you're doing is just one line long, if the function is one line long, you don't need to supply curly braces, as is fairly typical in most languages, but I habitually do it anyway. Okay, and so we've got this fn, let's define it to R. Something is wrong here. Unexpected blah. Oh my good heavens, I didn't say that it's a function, did I? Okay. That would be a problem. Okay, so I think that should be fine and dandy now. Let's say boot fn auto 1 to 392, which I think is everything, right? And we get the same results except back to digits 3. And now it's the same as the textbook's version. Okay, now the function can be used to create bootstrap estimates, so let's do that. And we're again using that special facility of sample, where we're sampling to get indices. That's right. And did I not set the seed? Yeah, I did not set the seed. And so I got different numbers. And now do I get the same numbers? Yeah, I've got the same numbers. Okay, now I can run that again and get different numbers. Well, I just did get different numbers. I run it again without setting seed again, I'll get different numbers, as I just did. And they've changed the digits again. Okay. So that's why they keep doing that. All right, so let's do boot auto, and we're going to use this new boot fn function in 1,000 bootstraps, and we will get, I can't even tell if it's the same results here. Yeah, I think it's the same result. It's just it's back to options is 3. Yeah. Yep. Slightly different standard error, but we basically got the same estimates. And just very slightly higher standard error. So the it's probably a result of not setting seed again. So now I get the same standard error. Okay. Not that that's a big deal. Okay, so and we can take a look at the. Oh, this is kind of interesting actually. Let's take a look at the summary LM MPG power data equals auto $COF. Right, and notice when we do this that we get somewhat different estimates here. Different estimates than what we got from the bootstrap. No, they look the same to me. What did I do here? We should be getting slightly different ones, everything. And we claim, oh, okay, so we're getting different values for the standard error. Is that right? Yeah, we're getting different values for standard error. Yeah, the standard error estimates are different. Okay, good. So, and the textbook asks us, does that mean that there's something wrong with the bootstrap? And in fact, what it means is there's something wrong with the linear model. So here we're using a linear model for something that we know to have a curved relationship. And so the linear model formulas rely on assumptions, rely on the variance of noise, the sigma squared parameter. So because they rely on that, and because there's a nonlinear relationship in the data, there must be an inflated picture of sigma squared. Sigma hat squared is going to be inflated beyond what sigma squared really is. So it's unrealistic. And one way to verify that is to try the more realistic data set. So let's do the same thing again, except we're going to compare it to well, let's see. Okay, let's say okay, so we're going to redefine this. We're going to redefine. Let me just say. We're going to redefine this to be horsepower plus I times horsepower squared, which is the other way other than the poly horsepower comma 2. to do this. And are we staying with the same subset? Yes. Okay, so we're going to redefine the boot function that way and set seed 1 again for replication of results. And then we'll run the bootstrap 1,000 times with boot fn as we did before. Only now we're bootstrapping a better model. So now we should be getting the same estimates or closer estimates than what we get from the same estimates or estimates that are closer to this model. And they're much closer. Yeah, they're a lot closer. We're getting the same ones as the, I think we're getting about the same ones as the textbook. Yeah. Yeah, we have the same ones as the textbook, and these are much closer. So the standard, what I'm saying is closer is the standard error estimates that we get here and here. These two standard error estimates are very close to these two standard error estimates here. Okay, and then that does it. That's the end of the first half of iste780. Thank you for your attention, and I look forward to the second half of our program.